Hello everyone, welcome to COMP359 Design and Analysis of Algorithms at University of Fraser Valley. In this video we are going to talk about divide and conquer, and mainly the focus of this video is to solve two famous problems that usually discussed in the in the area of the divide and conquer. So the whole idea of the divide and conquer approach is to solve problems by breaking it into a couple of other subproblems which are of the same type, and then combining the solution of those subproblems and get the answer for the original problem. You have already seen many, at least a couple of examples of problems that has been solved using divide and conquer approach. Among them, I'm sure you remember merge sort that we have actually discussed it last week, quick sort, which is also a divide and conquer algorithm, binary search, which is also a kind of divide and conquer approach. That in the binary search you only have actually one, you create one subproblem each time instead of more than one. In many cases you create more than one subproblem, but in binary search just one. So in this video I'm going to solve two other famous problems that we can actually create a good algorithm, efficient algorithm using divide and conquer approach. The first problem is counting inversions. So what is the problem? Assume that I have a sequence of n distinct numbers, and I'm looking for the number of inversion pairs. But what is an inversion pair? In a sequence of numbers, two items in the sequence, AI and AJ, will be called an inversion pair if the first item, A sub I, is coming before A sub J, so the value of I is going to be less than the value of J. It's just, the I and J will be the rank of the numbers in the sequence, and the value of AI is greater than the value of AJ. Okay, so let me give you an example. Assume I have a sequence of 5 items like 3, 7, 2, 5, and 4. And in this sequence, if you count, you can see that I'm going to have 5 pair of inversions. So 3 and 2, you can see that 3 came before 2 and it is greater than 2. 7 and 2, 7 came before 2 in the sequence and it is greater than 2. 7 and 5, 7 and 4, and the last one is 5 and 4. That still 5 is greater than 4 while it is coming before 4. So this is the problem. Before we get into solving it using divide and conquer, let me actually tell you about the use case of such a problem. So then counting the number of inversion pairs can be in fact very useful when you are checking how unsorted a sequence of numbers, a sequence of items which are in fact sortable, they are comparable to each other, are. So as the number of, you can actually think of it in this way, that of course if all the numbers are sorted in the sequence, the number of inversion pairs is going to be 0, right? And if the numbers are sorted in the reverse order, the number of inversions is going to be n to n minus 1 divided by 2 pairs. So basically all the pairs. This is, it's going to actually give you some kind of understanding about how unsorted and a sequence of items are. Or you can kind of use the number of inversions, this problem counting the inversion pairs, to compare two sequences and check how similar are these two sequences. if you are interested in this second actually case, you can refer to the Killenberg-Tardosh. I believe that is going to be the section, it is going to be in chapter 5, section 5.3. The Killenberg-Tardosh has been actually elaborating on this different use cases of this problem, which is very interesting. So now let's just discuss about how we can solve the problem. Before we discuss about that, the divide and conquer approach, let me just give you, I'm going to actually give you some moment. You can pause the video, think about the problem, how you are going to approach the problem, how you can actually solve the problem. The first approach, the naive approach that may come to mind immediately is that, okay, I am going to have a sequence of numbers, I have an array of items, numbers, and I can check all the inversion pairs by just checking all the items. For example, starting from, a loop I starting from 1, the second one j starting from I and going forward to n, checking all of these pairs and comparing them. If the value at the index I is greater than the value at index j, it's going to be an inversion pair, right? So clearly using a two-nested loop, by checking all of these pairs in the sequence, you can count all the inversion pairs. This is the, like we can call this kind of actually approach as brute force search, because you are checking every possible inversion pair and count them. You are checking every possible pair in the sequence. If they are inversion pairs, you would actually count them. So this is a naive approach. The complexity of that is going to be n squared. You have two nested loops, right? And are we interested in that algorithm? No. We wanted to see that using the divide and conquer, can we find a faster solution, a more efficient algorithm for this problem or not? Okay, let me clean this part a little bit more and use a different color that make it easier. Okay, so we are going to use a divide and conquer approach. The first thing that came to mind is that, okay, what would happen? How can I actually solve the problem in a divide and conquer approach? The first thing that came to mind in this approach is that let's divide the array into two parts. And okay, if I divide the array into two parts, it's going to be the first half and the second half. What I know about the total number of inversion pairs in the full array, in the original array, is that the number of inversion pairs in this side should be counted. The number of inversion pairs in this side should be counted. In addition to this, I also need to know all those inversion pairs that the first item is this side and the second item is on the second side of the array. Okay, I need to also look for this crossing inversion, let's just call them crossing inversion pairs. Okay, that a sub I is coming from this side, a sub j is coming from this side. So if you think about it in this way, solving this problem, this is exactly the same problem as counting the inversion over an array. So counting the inversion over an array of size half, counting the inversion over an array of size half, add these two and also count those inversion pairs that one of them is in this side and the other one is in this side. So this is the approach. This is a divide and conquer approach, which is going to be a recursive approach actually, right? Solving these sub problems needs to be actually done recursively. So Let's just this is exactly writing down all that I explained to you, that count the number of inversion in this side, count the number of inversion on the other half, and then the remaining problem is just counting those inversion pairs, which the first one is in the first half, the second one is in the second half. That's calling them cross inversion pairs. Okay, so no or problem will be, because actually solving the finding the inversion pair on the first half or finding the inversion pair on the second half, this can be done as a, for example, this is the recursive part of it, right? So what I need to solve here is the problem of count the number of cross inversion pairs. Okay, so now my question is that, is this problem, finding the cross inversion pairs, is easier than the original problem or not? This is an essential question, because if you, when you are trying to apply the divide and conquer approach, you should make sure that by applying the divide and conquer approach, you are making the problem simpler. If the problem of finding the cross inversion pairs is as hard as finding all the inversion pairs in the sequence, so what is the point? You just actually count the number of inversion pairs. You don't need to actually go to the hassle of using the divide and conquer approach. So this is an essential problem that whenever you try to apply the divide and conquer approach, you should ask it. But for the case of this problem, I'm trying, of course, the divide and conquer approach is going to make it easier. So no or question is that, otherwise I wouldn't actually discuss this example in this video. So this part of it is clear, but I'm just trying to say that for any new problem which is given to you, if you are going to apply the divide and conquer approach, you have to think about this, that after you apply the divide and conquer approach, that combination part, that when you get the solution for the sub problems, then you are going to combine those solutions. Are you really making it simpler, or the remaining part is still a very difficult problem? If it is still a very difficult problem, so maybe divide and conquer is not a correct approach to solve the problem. Okay, let's get back to our problem here, finding the cross inversion pairs. So to do this, one approach that came to mind is that, okay, what I can do is that I can sort both sides of the array, okay, and then try to count the number of inversion pairs. So this, the first half is sorted, the second half is also sorted, right? Now try to find the number of inversion pairs. So it's just like the number of cross inversion pairs. So it's just like for 2, how many items on the other half are going to be smaller than 2. For 3, how many items on the second half are going to be smaller than 3. So this is something that we need to count, right? So can we do it simpler if these items, all of them, are sorted or not? I believe this is going to be simpler, right? So for example, for 2, what you can do is that, because the other side is already sorted, what I can do is that just use the binary search, okay, to find the value of 2 on the other side. Of course, the value of 2 is not on the other side, but it gives you the position of the array, that all of the items from that position to the beginning of that sub-array, all of them are going to be smaller than 2, okay? And then, for example, for the value of 3, you try to find the correct position of 3 here, and then it's going to give you, for example, this position. All of the values less than this position are going to be, all of the values before this position are going to be smaller than 3 because this array is already sorted. Okay, is this problem simpler? This is simpler, right? Because what is going to be the cost for each of the items here? You are going to apply a binary search on the other side to find the number of items which are smaller than this specific item. So you have n items here. The cost of each binary search that you are going to do on the other side is going to be log of n. This is going to be half of the array, so log of n divided by 2. But we are ignoring those constants, right? So n to the log of n, the cost of finding cross inversion pairs is going to be n log n using this approach, assuming I have already sorted the arrays, this one and the first half and the second half. And so there is going to be a cost for sorting as well. That's going to be n log n as well, n log n plus n log n. So you can just assume that it's going to be the total cost here is going to be n log n. Right? That's better than n squared. Okay? So this is going to be the approach. This is the first method. Later on, I'm going to show you that we can do even better than this. So before I go forward, one thing that I can do for you is that, assuming that we are going to use that method that I have talked to you, this is going to be the full algorithm. So you can see that the algorithm that we wrote, we call it COMP359, right? That's going to actually count the number of inversion pairs. So I am going to have, this is going to be a recursive algorithm, of course. So this part is checking that if the size of the array is 1 or 0, of course there is not going to be any inversion pairs, so the algorithm will stop and return 0. So this is the base case for your recursive algorithm. And then you will call the counting inversion for the first half, call the counting inversion for the second half. You can say it's just return some values that you will keep it. Then you have to sort the first half, you have to sort the second half, and then you will actually count the number of cross inversions. Okay, that using the algorithm that we discussed, just use the binary search, and the cost of this one is going to be n log n. Okay, so this can be one algorithm, right? This is going to be the main algorithm. So the remaining part is just talking about this one, that even I can do it in less cost than n log n. So the second algorithm that I'm going to discuss to count the cross inversion is an extension of the merge method in the merge sort. Remember what we do in the merge method of the merge sort? You have two subarrays that both of them are sorted, and you are going to merge them and create a larger array which is sorted. So we have 3 pointers, one at the beginning of the first half, one at the beginning of the second half, right? And what we did in merge was that comparing the smallest item in the first half and the smallest item in the second half, whatever is going to be smallest, you will be smaller, you will be actually copying it in the new array. So here 1 will be copied, right? And then the pointer will be actually just updated, and you keep comparing and copying the next item in the new array. But what I can do here is that along the way that I'm merging, I can also count the number of inversion pairs. So at the first time that you compare the first item at the second half and the first item at the first half, what you learn by this comparison is that okay, the item which is smaller is coming from the second half, right? Not only you copy that item, but also it is telling me something, that this item is going to be smaller than not only 2, but also all the other items, remaining items in the first half as well, because already 2 is the smallest item in the first half, right? So 1 is smaller than 2, so it's going to be smaller than all other items remained in the first half as well. Okay, so assuming that, for example, I have n items here, and assuming that this index, let's just call it I, not J. And this item, let's just this index, let's just call this one, for example, J. So what will I know from this comparison? You will actually comparing, for example, the item at index, let's just say that the A1, the first half, for example, at index I is greater than A2. Let's just call this one A2 and this one A1. Okay, A1's index J. What I would understand from this is that all the items in the first array after the index I will be greater than the item A2 sub J as well. So how many of these items will be there? So for example, if that's going to be n minus I items remained in this array, that all of them are going to be greater than this item that I am actually working on, right? So I can keep, by doing actually the merge, during the merging, I can also keep counting these inversion pairs as well. So here at the first time, that's going to be actually 4 items will be added to the cross inversion pairs, not the full inversion pairs. So cross inversion pairs. And then the value of the index I will be actually updated. So for example, at the first time that was going to be, for example, 0, and then in the second time it will be, let's just actually put them all here. Index 0, for example, 1, 2, 3. So that's going to be, for example, n will be 4 minus 0, this many number of items in the second half will be greater than actually this value, right? And then the indexes will be actually updated. J will be referring to this one, and then you compare the value again, A sub I and A2 sub J as well. So this time the value of 2 is smaller than the value of 6. So I don't need to add any cross inversion pair, right? The value of 2 is smaller than 6, and I'm done. So 2 will be actually copied here. Then the value of I will be updated. It will be actually referring to this one. It's just killing here. Okay, the value of 3 is still smaller than actually the value of 6, so no inversion pair will be actually added. So the value of I will be, you keep updating the value of I, and then the value of 4 is still smaller than the value of 6. So I forgot to copy this one here. So 4 will be copied and no inversion pair because the smaller item is coming from the first half, and then the value of I will be actually updated to refer to this index, right? At this point you will learn that, okay, the value at index I is smaller than the value at index J on the second half. So in that case, again, how many there is going to be an inversion pair, and how many inversion pair will be actually there? It's going to be n minus I number. What was n? N was 4. I here is referring to this index 3. So one more actually pair because of having 9. which is greater than the value of actually 6. So it's going to be plus 1 again here. And what you are going to do is that this time you are going to be updating the value of j. Okay, so 6 will be actually copied here, and you will update the value of j. So this time again you are comparing this item and this item. Still, this item is going to be smaller than the value of n. So n minus I will be added to the number of inversion pairs. So another 1 will be actually added, right? Again, this item will be actually copied, 7 will be copied, then j will be updated. Still, this item is going to be smaller than this item, so again, another n minus I will be added to the number of inversions. So another 1 will be actually added, and then j, this item will be copied. You reach to the end of the items on the 1/2, so it's just like I'm done. All the items from the first half will be copied, and no more inversion is going to be actually added, no more inversion pairs, because I've already counted all the items on the second half. So how many inversion pairs, cross inversion pairs I have? All of this summation, which is going to be 7 inversion pair. So this method is exactly the merge method. I just actually extended it by counting, by adding this n minus I whenever you are copying from the second half. Whenever you find an item which is the smaller item which you are copying, it is coming from the second half, and that's going to be actually the method that you can do to count the number of cross inversions along the way that you are doing to the actually merging. So the cost of counting the cross inversions instead of n log n is going to be linear, which is going to be exactly the cost of merge. I just didn't really do anything more except that doing the merge and just also adding a couple of n minus I whenever I'm copying from the second half. So the original algorithm is the same. I just actually updated this part of it. So what's going to be the cost of this algorithm, the full cost of this algorithm? You can see that this is a recursive algorithm. I have T of n as the cost of the full algorithm. I have 2 call of the same algorithm, so for each of them is you are going to have T of n divided by 2, T of n divided by 2. They are going to actually do the half of the problem, solve the half of the problem. You are going to have some costs for sorting, right, and the cost for counting the cross inversion and merging. So if I'm going to write down the full algorithm, the cost of the full T of n, this is going to be the recursive relation for the time function. You can solve this one, and as an exercise for yourself, solve this recursion relation. But this is the answer that if you solve it, you should reach to this answer, theta of n log n power 2. So there are going to be 2 log n's here. But before we leave, I'm going to actually just tell you one thing. Don't you think that we are doing some repetition here? Don't you think that this algorithm is very similar to the merge sort algorithm? And do you really need to do the sorting each time inside this recursive algorithm? In fact, not. What I am doing this, if I remove this sorting part, nothing would happen to the algorithm. Why? Because this algorithm of merge and count cross inversion is doing the merging over the array, right? And these two recursive parts are going to be actually exactly like the doing the merge sort. So I don't really need to explicitly sort the arrays, because along the way that I am dividing the array into two parts and merging and counting the cross inversions, I am sorting the array as well. Okay, so array will be sorted in this approach, in this recursive algorithms. I don't really need to explicitly sort the array inside the recursion. So these two parts can be simply just removed. What will be remain here is going to be just a recursive algorithm, very similar to the merge sort. The only difference here is that inside the merge method, you also count the cross inversion pairs as well. The rest of it is exactly similar to the merge sort. So the new algorithm will look like this, that instead of count inversion, I will call it count and sort. So you are doing the merge sort and you also count the inversion pairs as well. So for this algorithm, if I write down the time complexity, the analysis over this one, this is going to be exactly similar to the merge sort. T of n, you have some base case here, the same function call here, the same function call here over half of the array, and you are going to have the cost of linear for doing the merge and counting the cross inversions. So the total recursive relation is going to be T of n equal to 2T of n divided by 2 plus O of n, and the cost is going to be O of n log n. This is exactly similar to the time complexity of the merge sort. So this is the discussion about the counting inversion. As an exercise, you can try to write down the the full pseudocode for the merge count cross inversion method, just very similar to the algorithm that I gave you last week. Just try to extend that and also count the number of cross inversions, and then try to implement it in any programming languages that you feel more comfortable with. This is going to be a very good practice for your even for the interview of the job or co-op, that if you are going to take, these are very good practices for them as well. The second problem that we are going to solve here is the maximum subrange sum problem. So what is this problem? Assume that I have an array of items. So I'm not giving you any information about the items, so they can be actually positive, negative, anything. What I'm looking for is a sub-array in this array that has the maximum summation. So when I'm saying a sub-array, this is going to be a continuous part of the array. So if I write the problem in math, this is going to be finding the two values of I and j, where the summation of the items from index I to index j is going to be maximized. I am looking for these two pairs. So in fact, I'm looking for a part of the array where the summation of all the items from inside that part, the continuous part of the array, where the summation in that part is going to be maximum along all the possible sub-arrays in this given array. So you can actually pause the video and try to work over an example. Look to this array and try to find a sub-array in this array which has the maximum summation. So if you find the answer, that's going to be this part of the array. If you check, you will see that you cannot find any other part of the array that has the largest sum larger than actually this value that we have here. This is going to be the optimal solution. So before I gave you the the algorithm, let's just actually just briefly talk about the use cases for this problem. Although the problem doesn't really look very practical, but there are very interesting applications for this problem in biology. So sometimes in a sequence, in a DNA sequence, the biologists are looking for some specific part of the sequence. For example, I am interested in a part of the sequence that a continuous part of the sequence that the number of G and the number of C's in that part are greater than the number of A molecule and T molecules in that part. Okay, this problem doesn't really look like the Subrange Sum, but I can convert it to Subrange Sum problem. How? I will actually put 1 instead of all the G molecule and instead of all the C, and I will put -1 instead of all the A and all the T. So the DNA sequence will be converted to a sequence of items, an array of items like this. So if you think about it, the problem of finding a part of the sequence that the number of G's and C's are greater than the number of T and A will be exactly the problem of finding the maximum subrange sum, right? Because for each G and C you have 1, for each T and A exactly you are going to have -1, sorry. Okay, now let's actually think about how we can solve this problem, the maximum subrange sum. The naive algorithm that came to mind here is that, okay, I will check all the possible subarrays. Then I will calculate the summation for each of them and find the maximum one. This can be done simply using a pseudocode like this one. You can see that I have 2 nested loops for I and j to check all the possible subarrays, and there is another loop that calculates the summation, and for sure you're going to find the optimal answer using this pseudocode. But is it a good algorithm? It's not. If you think about the problem, you can see that the time complexity for this actual algorithm is going to be n cube, right? I have 2 nested loop here, and I have another linear loop here as well. That's going to be n power 2, and that's going to be actually another linear actually cost here, and it's going to be n cube. This is not very efficient. In fact, this naive algorithm, which is, we call it brute force algorithm, because we are checking all possible answers to find the optimal answer, is not a very appealing algorithm, of course. Before we leave, I am going to actually tell you something. I can modify this algorithm and get something better than this just by removing this loop. Do I really need to calculate the summation of all these subarray sums explicitly using a separate loop? The answer is no. In fact, you can modify the algorithm and write it in this way. That along the way that the value of j is going forward and you check the next subarray, you can also calculate the summation and update the summation. So I don't really need to separately calculate the summation of the subarray inside these 2 nested arrays each time, because we are doing really a lot of repetition here. I can modify that algorithm and do it in this way. So each time that the value of j, so look like this, it's going to be something like this, that the value of I, so whenever for example this is I, this is referring to this part of it, the value of j will start it from the value of I and go forward as the value of j will be updated. It's just like I am adding one more actually item. So I'm checking this sub array first, and then I will check this sub array, and then I will check this sub array, right? So as you go forward, the summation over this sub array and then the summation over this sub array, it's just like the summation of this sub array will be the summation of this sub array plus this item. So this is exactly what I can do over this algorithm. So this is going to be a modification of the previous naive algorithm, and you can see that even that naive algorithm can be modified, and this time instead of n cube I can actually do it in n power 2, in n square. I just need 2 loops to do the full calculation. It gives me the optimal answer, of course, but I'm looking for something better than n square. How can we do it? I am going to use the divide and conquer approach. So how are we going to deal with the problem using the divide and conquer approach? Let me just give you this, this fact about calculating the subrange sum. So when I'm thinking about the divide and conquer over an array, the first thing that came to mind is that let's just divide the array into 2 halves and see that if applying the same problem, solving the sub problems are going to help me in solving the final solution or not. Just like something that we did in the counting inversion, that the first half and the second half, we actually counted the inversion pairs on the first half and the second half, but some part of the problem remained counting the inversion pairs in the cross inversion pairs. I'm going to actually try to see that what I understand from this problem. This time I'm not looking for counting something. I'm looking for, the maximum subrange sum. So if I divide the array into 2 parts, I will have 3 possibilities for the maximum subrange sum. So if I divide the array into 3 parts, this is going to be first half, this is going to be second half, right? And I'm looking for the maximum subrange sum. The maximum subrange sum over the original array, it is going to be, there are going to be 3 possibilities for that. The first possibility is that it is in the first half. So your maximum subrange sum can be either completely actually here, or it can be completely on the second half, or it can be something which is passing the midpoint, right? Something that is passing the midpoint. Let me actually just, give you a better sense of it. So it can be actually anywhere, but somewhere that it is passing the midpoint. I didn't actually make it any better, but it's just like one part of it, not, not half of it on this side, half of it on the other side. So it can be some part of it on the second half, some part of it on the first half, right? And these are going to be all the 3 possibilities that I have. So this is going to be the first possibility. This is going to be the second possibility. In the second half. My handwriting is really bad here. It's just okay. Crossing the mid point. Okay, Okay, these are all the possibilities that I have for the maximum subrange sum in the original array. So still you can see that finding the maximum subrange sum in the first half and in the second half are going to help me in solving solving two cases of these three possibilities that I have. But the last case is something that I have to solve it directly. This is not going to be done, it's just like this part and this part are the recursive part of the solution, and this part is something that I have to solve it as, to be able to solve the full problem. So now the question here is that, is it easier to find, the subrange sum which is passing the crossing point? Because I'm sure that if I'm looking for the answer for the full array, I have to solve this one, I have to solve this one, and I have to find this one as well. Then compare all these three possibilities and find the optimal solution, find the one that has the largest sum, and that's going to be the final answer for me. So all of these three cases needs to be actually calculated to be able to solve the full problem. So is it easier to find the subrange sum which is passing the midpoint? Is it easier than the original problem? Can I do this in the cost less than n square, because I have already actually solved the full problem in n square? Can I solve this problem in less than n square or no? If you can't solve this problem in less than n square, so you should not think about the divide and conquer. At least you should not think about this approach for the divide and conquer. So now the problem that I'm going to solve here for you is this problem, finding the maximum subarray that is crossing the midpoint. There is a very interesting fact about such a array. And that fact is that because you have to check all the subarrays that is passing the midpoint, so some part of this subarray will be this side and some part of it will be on this side. And it's just like I'm looking for some suffix of this array, and I'm looking for some prefix of this array. So this is not going to be the regular subarray over this array, because I am fixing one side of each of these problems. So the problem will be actually converted to finding the maximum suffix over this array and finding the maximum prefix over this array. Then you will actually just merge these two, and it's going to give you the maximum subarray which is crossing the midpoint. Okay, this is the key point to solving the problem. Now the problem is, how can I calculate how can I find the maximum suffix over, for example, this part, or maximum prefix over this side? What is going to be the time complexity, and how can I actually do this calculation? Is it easier than n square? It is. I can do the job. I can find the maximum suffix here in linear time, and I can find the maximum prefix here again in linear time. Okay, now let me solve the problem of finding the maximum suffix over in an array, finding the maximum prefix in an array. Let's just see that if I can clean all this. Okay, delete all this. Even actually I can delete this one and delete this one. Okay, you have an array. I'm going to actually talk about this problem, that you have an array, you are going to find the maximum suffix over this array. So if you are looking for a maximum suffix over an array, that's going to be either this one, or this one, or this one, or this one, or this one, right? So it's just like you are checking all of these summations. How can I do that? I can do it using a very simple loop. From I equal to n, from n to 1, you just need to calculate the sum and keep updating that, and you can also define some max to be 0 as well, and you actually go down. I is from n is approaching to 1 and checking the summation for this part, for this part. So it's just like you just add up array index I to that, and each time checking that if the max is smaller than the sum, you just update the value of that max. Let's just call it max. It can be whatever you would like to call it. That's going to be the value of the sum. So you need to, in fact, check all of the prefixes, but checking that can be done in O of n. Sorry, all of the suffixes. Checking all of that can be done in O of n. And very similar to this, you can calculate the maximum prefix. This time you started from 1 and going forward and checking all of these summations and finding the maximum prefix. Okay, so the problem of finding the maximum subarray which is crossing the midpoint will be converted to finding the maximum suffix in the first half, finding the maximum prefix in the second half, and you just need to add these two answers, and that's going to be the answer for the subarray which is passing the midpoint. Now I will actually put all of this is that the pseudocode for finding the maximum suffix, and I will add all of this, put all of this together in the final divide and conquer algorithm for the maximum Subrange sum. So this algorithm again is going to be a recursive algorithm. I will need some base cases for the algorithm to stop. So whenever the size of the array became smaller than the 0 or 1, it will stop. So these two cases are just covering that. And this is again very similar to what we write for the merge sort. So it is going to have two sub problems of the same type, but the size of it is going to be n divided by 2. Another solving actually the subarray in the second half, that's going to be a problem of size n divided by 2, right? And these two parts are going to be just finding the maximum suffix and maximum prefix that you need to actually just add them together to give you the maximum subarray which is crossing the midpoint. And then at the end you just compare these three solutions, either a crossing point, or it is in the first half, or it is in the second half. Whatever is the answer, you will return that. So what is going to be the time complexity here? The time complexity here will be linear for calculating the maximum suffix and linear for calculating the maximum actually prefix, t of n divided by 2 here, t of n divided by 2 here, and the rest of it is going to be just constant there and constant here. So the relation is going to be exactly similar to the merge sort. Of course, if we solve such a recurrence relation, t of n equal to 2 t of n divided by 2 plus O of n, the answer is going to be n log n. So this is the divide and conquer approach to solve the maximum Subrange sum, and we could actually solve it better than that n-square algorithm, the naive algorithm that we had. Just one point before we finish this video is that in fact there is even a better algorithm than n log n to solve the maximum subrange sum. It is possible to find the maximum subrange in an array in a linear time. There is a linear time algorithm for that, but that linear time algorithm is not going to be a divide and conquer approach. That is a completely different actually approach. I have written the full algorithm for you here, but because this is not the divide and conquer approach, I'm going to skip it and just leave it for you to read it. If you had any question about it, we can discuss about it during the office hours or in in class if you had more question about this one. So I'm going to actually stop the video here, and in another video we will solve another two problems using the divide and conquer approach.